In this video, we're going to talk about polynomial functions of a higher degree. So polynomial function of x with degree n is this function where a of 0 through a of n are real numbers, a of n is the leading coefficient, and n is a non-negative integer. So I've written examples of polynomial functions and examples of not polynomial functions. Notice the examples of not polynomial functions. It is the exponential powers that are not non-negative integers, such as 1/2 for the first one and -4 for the second one. Okay, now I want to talk about the degree of each polynomial function. Well, the degree for f of x, remember it's separated by addition and subtraction, so whichever term has the highest exponential power is going to be the degree of the entire polynomial. So the degree here is 4. Okay, let's take a look at two other examples then. Let's take a look at I of x here. Now again, notice this is not separated by addition and subtraction right now. In fact, it's multiplication. So what do I have? I've got x to the 5th here. What's the highest exponential power I'm going to get with this? Well, that's x to the 6th, because x cubed taken to the 2nd power, you multiply the exponents. That gives you 3 times 2, which is 6. And same idea here, x to the 8th. Because it's separated by multiplication, I add the exponential powers. So 5 plus 6 plus 8 is 19. So the degree of the polynomial here is 19. Keep in mind, I don't want to expand it out and multiply. That takes too long. I just want to know what the degree for this function is going to be. Okay, for the last example on this page then, similar idea that I can use above. I've got x to the 9th. The biggest this is going to be is x squared, and the biggest here is x to the 12th. Again, when I multiply exponents, I add the powers. So 9 plus 2 plus 12 is 23. So the degree here is 23. Okay, so let's talk about polynomial functions then. These are simple functions that are continuous and smooth. A continuous graph is a graph that has no jumps or holes. And a smooth graph is a graph that has no sharp edges. So I've drawn examples below. The one on the left is a graph that is smooth and continuous. These are what I would expect our polynomial functions to be. Okay. The middle example shows that it has holes or jumps. That is not going to be a polynomial function. In fact, that's a piecewise function. We've already graphed those. Okay, and it's discontinuous at x equal to 1. But you're not going to have any graphs that have sharp edges like the absolute value graph. Okay, in order for us to do polynomial functions, it would be nice to know what the zeros or the x-intercepts of a function are going to be. Okay, so the real zero of a function are x-intercepts of a function. So the 4 statements below mean exactly the same thing. So x equal to a is a solution or root for f of x is equal to 0. A comma 0 is an x-intercept for the graph f of x. X equal to a is a 0 of the function f of x. And x minus a is a factor of f of x. All right, so now I want to be able to identify the real zeros. So again, the first thing I will do is I will replace f of x with 0. All right, so then from here, I'm going to factor out an x. And then I'm going to factor the trinomial. Well, factors of 12 that add up to be -7 are -3 and -4. Set each factor that contains a variable equal to 0. Okay, 0 equal to x is done. So 3 is equal to x and 4 equal to x. So my zeros then are 0, 3, and 4. Now, make sure that you know x minus 3 and x minus 4 are factors. And then when I write 3 equal to x and 4 equal to x, like I did earlier, those are zeros. There is a relationship between factors and zeros to factors. We'll discuss more of that later on. Okay, so let's do one other example for this. Now, notice here, g of x, I'm going to still replace g of x with 0. Set each factor that contains a variable equal to 0, because notice there's nothing to factor here. All right, so for the left, I'm going to take the square root of both sides. That's plus or minus 0, but that's still 0. And 3 is equal to x. But notice, in reality, I would have a solution of 3, comma 3, because it's x minus 3 squared. Okay, for the middle one, take the cube root of both sides. That's still 0. And that's negative 3/5. In reality, that's this, and this, because it's cubed. All right, for the third one, I can take the 10th root of both sides. Again, doesn't matter. That's still 0, and that's 12. So, in reality, I have 10 different solutions of 12. Now, notice, in g of x's, zeros are repeated multiple times. This is what is called the multiplicity of 0. Okay. So the multiplicity of 0, if x minus a to the n is a factor of the polynomial of f, then a is called a 0 of multiplicity n of f. So from the previous example, 3 has a multiplicity of 2, 12 has a multiplicity of 10, and negative 3/5 has a multiplicity of, that should be 3 and not 2. All right. So let's go to the next page then. So one way that I could graph general polynomial functions is as follows. I could calculate the x and y intercepts, and I can break the graph into intervals using those x-intercepts, and then I want to find a point that is in each particular interval. Okay, so let's start with this. Let's start with the x-intercepts. We know with the x-intercepts, we know f of x is 0. So it's this. All right, so again, I can separate. So again, -1 multiplicity of 1 and 3 multiplicity of 2. I'm going to get into the habit of writing that out for us. Okay, the y-intercept. I'm going to scroll down a little bit so we can do this. Y-intercept, we know x is 0. So f of 0, well, 0 plus 1 is 1. And 0 minus 3 squared, that's 9. And 1 times 9 is 9. So the y-intercept is 0, 9. Okay, so I'm going to label my coordinate plane with my slashes. Okay. I'm going to get rid of the y and write this f of x. Okay, so now what I would like to be able to do is to plot -1, 0, and 3, 0, and 0, 9. Now, because this is a polynomial function, we know it's going to be smooth and continuous between -1 and 3. In fact, it's going to be smooth and continuous everywhere. But I would like to know what is happening before -1 and what is happening after x equal to 3. So let's plot, or let's solve for -2 here. So -2 plus 1, that's -1. -2 minus 3 is -5, and -5 squared is 25. So that's -25. Well, we can figure out then very, very quickly, we'll put this point way, way down here, that looks like it's going to go down forever. Okay? Now, what is happening after x equal to 3? Well, let's do f of 4. So 4 plus 1 is 5. 4 minus 3 is 1. 1 squared is 1. And 5 times 1 is 5. So that's 4, 5. So that looks like it's going to go up forever. So let's connect the dots. So there would be my sketch of this polynomial function. Now, what I would like to do is to see what it looks like using Desmos. So let's go to the graph. And you can tell with Desmos and my graph that they are very, very, very similar. All right. Now, what I would like to be able to do is now talk about how the multiplicity of a zero can help determine the behavior of the graph of a function. Now, what I would like to be able to do is to use Desmos to help me out with this. All right, so now what I have done with Desmos, I'm going to get rid of this. I'm going to put this graph on here. Okay? Now, take a look. I'm going to play with x plus 1 to the 5th power. Now, I'm going to change this particular exponential power to a 3. But notice, the 0 remains exactly the same, okay? And it looks like it's still crossing. Let's try it to the 1st power. Well, no, let's try it to the 7th power. Still crossing. Let's try to the 9th. Still crossing. So, when the multiplicity is odd, it is going to cross at the point A0. Okay. Now, let's talk about it being even then. So let's go back to Desmos again. Now again, notice with x minus 3 squared for this. Okay. Notice it is coming down and going back up. Let's try to the 4th. Again, you can tell it's coming down, but it's going back up, never crossing. Let's try to the 6th. Exactly the same. Let's try to the 8th. Exactly the same. So when the multiplicity is even, let's go back to our sheet, then it's not going to cross at A0. What I refer to it as it will kiss at A0 and go in the opposite direction. Okay? So again, the multiplicity, whether it's even or odd, will let me know exactly the behavior of that particular point at that particular spot. Now, the other part I would like to talk about is what is called the end behavior. The end behavior is what happens to the range values as x approaches positive infinity and as x approaches negative infinity for this. Okay? So again, what I would like to do is to go back to Desmos to show what is going to happen. Now, there are two things we need to consider, both the degree, whether it's even or odd, and whether the leading coefficient is positive or negative. All right, so let's go to Desmos then. So notice here I have x squared. Okay? Now, the leading coefficient is positive, and the degree is even because the degree is 2. Okay? Now, notice that the graph is going up in both directions. So as x approaches negative infinity, the range is approaching positive infinity. And as x is approaching positive infinity, the range value is approaching positive infinity also. Okay? So we can go back to our sheet then momentarily. So we want to look for what? The degree even and the leading coefficient being positive. So as x approaches negative infinity, f of x is approaching positive infinity. As x is approaching positive infinity, f of x is still approaching positive infinity. And the graph shape is going to be up and up, similarly to the parabola. Okay. Now, I now want to take a look at the second column. Now, what ends up happening if the leading coefficient is negative? Well, that's easy to show on Desmos. Okay, let me get rid of this for you. Now notice, as x is approaching positive infinity, f of x is going to negative infinity. And as f of x is approaching positive infinity, f of x is still approaching negative infinity for this. Okay, so let's go back to our table then. Okay, so the second column we're going to work with, as x approaches negative infinity, f of x is going to approach negative infinity. And as x approaches positive infinity, f of x is approaching negative infinity. And this time around, it's going to go this and this. So notice, if the degree is even, the end behavior directions are going in the exact same directions, either both going up or both going down. Okay, now let's take a look at the third column. Now we want a function with an odd degree and the leading coefficient being positive. Okay, so let's go back to Desmos then. So I'm going to get rid of this, and I'm going to do x cubed. Okay, now as x approaches negative infinity, f of x is approaching negative infinity. And as x is approaching positive infinity, f of x is also approaching positive infinity. This time, notice the end behavior direction arrows are going in opposite directions. Okay? All right, so let's go back to your sheet then. So again, as x is approaching negative infinity, f of x is approaching negative infinity also. As x approaches positive infinity, f of x is approaching positive infinity. And the directions are going to be this. Now, fourth example I want to take a look at is, let's do the degree being odd and the leading coefficient being negative. Okay, so let's go back to Desmos. So again, all I'm going to do is put a negative. So again, as x is approaching negative infinity, f of x is approaching positive infinity. And as x is approaching positive infinity, f of x is approaching negative infinity. And by the way, if I did x to the fifth, end behavior direction arrows, same thing. X to the seventh, same thing. X to the ninth, same thing. Does not matter. Okay? So let's go back to your sheet then. So again, let's fill this in. As x approaches negative infinity, f of x is approaching positive infinity. And as x is approaching positive infinity, f of x is approaching negative infinity. So that would be this and this. So we're going to use this idea of end behavior and the multiplicities to help us craft polynomial functions in the next video.